for lesson 3, we're going to be talking about triangle similarity rules. These are shortcuts to prove that triangles, specifically triangles, are similar using the least amount of information possible. We talked about on day 2 similarity in general. So we might have pictures like this, where we had congruent angles. I know that's not 90 degrees, but we have random angles like this. We can see that all of the corresponding angles are equal to each other. We would have all of these sides be proportional, right? So these are half the size of these. So the 2 and the 4, the 4 and the 8, the 2 and the 4, the 4 and the 8. All of these particular pieces that we have, all this information in the picture, all the angles are congruent, all the sides are proportional. We had all that information kind of knit together to decide whether our shapes were similar or not. What we're going to be talking about today is when we don't have all of that information, we don't have all of those sides, we don't have all those angles. What can we do if we have minimal amount of information? So that's how we come up with these 3 rules that can help us. So these are going to look very similar to the big 5 rules that we had in Unit 4, where we're proving that triangles are congruent. So it was like the side, 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 angle, side, angle, side, angle, 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 side, and HL. Those are exclusively for proving that triangles are congruent. It's very important you not mix those up with these. Those 5 rules we talked about before, and when you're trying to say that these triangles are identical to each other. These 3 rules are trying to say that the shapes are similar. The triangles are the same shape but different sizes. That's what these are for. So there are 3. We have angle, angle, side, 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 and side, angle, side. So these 2 look very similar because we had a side, 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 and side, angle, side for Unit 4, but they are going to work very differently. It's important you guys are able to distinguish them. So this one, which is unique similarity, that's the angle, angle rule. So angle, angle, or angle, 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 3 angles does not work for congruency, but it will work for similarity. So 2 triangles are similar if they have 2 pairs of corresponding congruent angles. So you have 2 pairs. You can have 3, that's fine, but you need to have at least 2. So I'll just make this little note, it's 2 to 3, but it's still officially called the angle, angle similarity rule. So here's an illustration. I have these 2 angles are equal, so I have O and L are congruent, H and C are congruent. So with those 2 pairs of angles that are congruent, that makes these triangles similar by angle, angle. Okay? You guys will still be expected to write a similarity statement. So that's just saying that this shape is similar to this one. You're going to name your first triangle in whatever order you want. The little squiggle stands for similar to, and then you have to name the second triangle so that it matches the spelling of the first one. So H corresponds to C, O corresponds to L, and T corresponds to D. So I would name the other triangle CLD. So that's angle, angle. Next up is side, side, side similarity. So side, side, side for Unit 4 is when we said that all 3 pairs of sides are congruent. But because we're working with similarity, the sides aren't congruent, they're proportional. So for this side, 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 2 triangles are similar if all corresponding sides are proportional. Okay? So we're going to compare the corresponding sides. We're not going to have markings anymore. In Unit 4, we would look at markings to match up the markings and see if we had 3 pairs of corresponding congruent sides. But again, that was Unit 4, we're leaving that behind. For side, side, side similarity, you actually need to have numbers. We're going to be using numbers to check to see if they're proportional, so you need to write them in ratios to check. So you'll notice that in these pictures, there are no angles first of all, because side, side, side doesn't involve any angles. It only has sides, and you have all 3 sides available in each triangle. So in order to write the proportion, you need to know what sides are corresponding. So it's a really easy system you guys want to use. You want to compare short to short, medium to medium, and long to long. So the shortest side in one triangle should correspond to the shortest side in the other triangle. The medium side in one triangle should correspond to the medium side in the other triangle. And then the longest side for the first triangle should correspond to the longest side in the other triangle. So when you guys are writing these proportions or comparing sides to see if they're proportional, you would just use this system. So for example, if I'm over here, the shortest side is 3AB, And then the shortest side over here is the 4.5. Excuse me, the PR. Sorry, PR. So I compare AB to PR, and that is 3 over 4.5. I can write that down. Then if I'm comparing the medium length sides, that would be 4, because the medium of 3, 4, and 5 is 4. So that's side AC. And then I compare that to the medium over here, which is the 6, which should be side PQ. So that's my second ratio here. So I compare 4 to 6. And then the longest side over here is 5, and the longest side over here is 7.5. If you were to put all 3 of those fractions into the calculator, you get the same result, the same decimal, the same value. So all of these are the same. That's the definition of proportional, is when you are writing these ratios between corresponding sides and all of the ratios are the same number, same value. So that's why it would be similar by side, side, side. And so the similarity statement for this one, A, which is this corner between the short and the medium, corresponds to P, C corresponds to Q, and B corresponds to R. So that's how you would get the similarity statement for those triangles. Lastly, we have side angle side similarity. So two triangles are similar if an angle, one angle of a triangle is congruent to the corresponding angle of the other triangle and the sides including these angles. That means that they're the two sides that are on either side of the angle. Those sides are proportional. Remember, anytime we're working with similarity, anytime you're working with sides, they're proportional. Okay? Not congruent. Angles are congruent, sides are proportional. So in this scenario, we do have an angle involved. So the angle, we have that sandwich, just like we did for Unit 4. You have to have two sides with the angle in between them. And so the angles would be congruent, the sides would be proportional. So in this picture, you will still have to add information sometimes. So in this picture, I would add the vertical angles. That gives me my A for the side angle side. And then I have two sides here and two sides here that are containing the angle. So I can see that it has that pattern for the side angle side. So I just check really quick to see they're proportional. So I compare short to short, medium to medium, or long to long. So I compare 2 to 3, and then 2.5 to 3.75. When I put either of those, sorry, that's a 2. There we go. If I put both of those ratios in the calculator, they would give me the same value. That means that they're proportional. So that means that the triangles are similar by side angle side. For each triangle, you can see that you have that information. So if I call the first triangle EST, then I would name this one ASD. You can kind of see how if this is the short side and this is the short side, you can see how they alternate. The E corresponds to A. So you can use the little information in the picture and the markings and the numbers to figure out what parts are corresponding. Okay, so those are our rules. Angle, angle, side, 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 and side, angle, side. So we're going to try to see what happens when we practice with these examples right here. So I'm going to look at this one. The best way to approach these questions is to look at what information you have and decide which rule you want to try. So like for this one, I don't see any side lengths. If you don't have any sides, you can't check to see if the sides are proportional, because you need numbers to do that. So for this one, because I'm missing sides, the only rule I can attempt is angle, angle. That doesn't guarantee angle, angle is going to work. It just means that's the only one I can try. It narrows down your work that you're focusing on. So I need to see if I have two pairs of congruent angles. I see that I already have one with the 40s. Now it doesn't look like I have a second set of congruent angles, but that's just because I don't have enough information right now. But I can add information. I know that because I have these two angles right here, and all three angles in a triangle add to 180, I can do a little bit of math using the triangle sum theorem, and I can figure out that this angle is 68. I can add the 72 and the 40 and then subtract that from 180. That gives me 68. So there's my second pair of congruent angles. So I have one and then two sets of congruent angles. So I would have similar triangles by angle, angle. There you go. That's all you have to do. This one right here, I noticed that I have two sides per triangle and then the parallel lines. Remember that parallel lines are going to give you an angle relationship, either corresponding or alternate interior for these ones, just like we saw in Unit 4. So because I have two sides per triangle and potentially an angle in between them, I'm going to be checking to see if side angle side works. Okay? Now, it's a good idea to physically draw that Z. Remember when you have that Z kind of shape with the parallel lines and the transversal, you're going to have alternate interior angles at the corners of the Z. So So I have those, that's my A for the side angle side. I do have that right there. And I do see that the sides that I have in each triangle are surrounding that angle set is my side angle side pattern. So all I need to do now is check to see if the sides are proportional, and then I'm gold. So I'm going to erase this just so it's not blocking the numbers. So what I want to do now is compare, again, short to short and then long to long with my sides. So the short side in the upper triangle is the 13.5. The short side of the bottom triangle is the 18. That's my first ratio. The longer side of the upper triangle is the 18 again, and then the longer side of the bottom triangle is the 24. Now what's interesting with this right here, this still uses the reflexive property because they are sharing that 18, but what's interesting in similarity is that the side that's marked 18, it is serving different purposes for the different triangles. On the top triangle, the 18 is the longer side, but on the bottom triangle, it's the shorter side. So they're sharing a side, but it's serving different purposes. So we can't quite use the reflexive property the same way for similarity. But when you guys check, we have the 13.5 over 18 and then the 18 over 24. If you guys put those in your calculators to check the numbers, I do believe they come out to the same. Let me just double check really quick. Yes. Yep, they end up being the same number. So that gives me my two pairs of sides that are proportional with the angle in between. So these would be similar by side. All right. Now we're going to take a look at this third one here. So this third one, they are separated. So when the triangles are separated, you're not going to be able to add any information. So we have to work with just what we have. So I see that I don't have any side lengths. I only have angles. So I'm going to be testing angle, angle. Let's see if that works. So I have one set of congruent angles here, but I only have the 30 here. I mean, technically I could add the 60 here if I wanted to, but I can't add any information on this triangle because I don't have a second angle, so I can't use the triangle sum theorem. So I only have one pair of congruent angles, and that's not enough. I can't just say A. Like, there's no rule that's A. It has to be angle, angle. You have to have at least two pairs of congruent angles. So for this one, I would have to say no, I can't prove that they're similar. Your reason for this one would be not enough information. Just like we had that kind of reasoning for Unit 4 with our congruency, that can show up again here. They might be similar, we just don't know because I can't find any of those angles in the other triangle. So we just leave it with any X. Alright, there we go. Alright, this one over here, obviously we're going to be testing side, 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 because I have all three sides in each triangle and no angles. So again, for side, 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 you're going to compare short to short, medium to medium, long to long. So the short side over here is 11, compared to the short over here, which is 19. Then we compare 15 to 20, and 18 to 24. So when you stick these in your calculator, you'll notice that these two are the same, but the 11 over 19 throws everything off because the 11 over 19 is not equal to the other two. So when you have that happen, where one of the ratios is not the same as the others, you would have to say, no, they're not similar. And it's not because there's not enough information. We have plenty of information. We had exactly enough information. It's just that the information that we had provided didn't work for the rule. So when I asked for a reason, you guys would say, no, they're not similar. And you'd say, because side, side, side fails. The rule fails. So when you guys answer no, there are two reasons why you would get follow up or explain why. It's no, I can't prove they're similar because there's not enough information, or no, they're not similar because the rule I used didn't work. Okay? Alright, for this one, it's going to be helpful for us whenever your shapes are up against each other like this, but it's not the reflexive property, or even if it is, it's usually a good idea to separate them because it makes it easier to work with the numbers. So I'm going to go ahead and draw these shapes separate from each other. Oops. I'm going to be better than that. There we go. Still not better. And then a smaller one. And then I'm going to label them separately. So I have the 5, and then I notice that this side right here has the 6 and the 4 combined. So this is really 10. And then this is 6, and this is 3. And then while they were together, I noticed that I had one right angle here. So I can use linear pair postulate or the perpendicular definition to say that this is also a right angle. So I have this right now. So with that information, this is implying we're going to be trying the side angle side rule. Okay? So I need the angles to be congruent, I need the sides surrounding the angles to be proportional. So I know the angles are congruent because they're both 90. So we know those are congruent. Now I just need to check to see if the sides are proportional. So I'm going to compare short to short, long to long. So 5 over 3 compared to 10 over 6. Notice I'm going from one shape to the other and then going back to the original and repeating that pattern. So 5 over 3 is the same value as 10 over 6, so they are proportional. So that would mean that these shapes are congruent by side angle side. Okay? The last one on this page, this one's a tricky one. I know you guys are going to be tempted to think that we're going to be using side angle side because you see the markings here, and then an angle there. But we actually can't use side angle side for this one. To use side angle side or side side side, we need to have, first of all, you would need to have the markings be the same in order to compare them. But this is one hash mark and this is 2. But more commonly, you need numbers. In order to check to see if they're going to be similar, you need to use a proportion to check that, so you need numbers to check that. And so because this one has a clear absence of numbers on the sides, we can't use the sides. So all that we're left with are the angles. So we're going to have to be stuck testing angle. At first glance, it looks like we don't have enough information for angle, but you do have to notice what's going on with the markings here. Each triangle separately have 2 congruent sides marked. So that means that they're isosceles. Hopefully you guys remember from previous unit we had the isosceles base angle theorem that says if you have 2 congruent sides, you have 2 congruent angles. And so if you look at each triangle, these are the congruent sides of this triangle, so that means that the base angles here at the base of the triangle are congruent. So I knew that this one was 71, that makes that one 71. Okay? You could also use the triangle sum theorem, and you can get that if these are both 71, that will leave you with 38 as the vertex angle. Well, if you look over here, this is another isosceles triangle with a vertex angle of 38. So if you did the exact same process to find these 2 angles, P and Q, you would have to do 180 minus 38 divided by 2, and that gives you your 71s again. So these are both isosceles triangles with the same angle measurements. One is just a dilation of the other so that it's smaller. So you could either choose the 71s, you could choose the 71s and the 38, whatever you guys want to do. As long as you have at least 2 pairs of congruent angles, they're going to be similar by angle. Now before I go on to the next page, I do want to mention really quickly, any triangles that are congruent are also similar, but it's not true the other way around. So if you think carefully, like if I gave you this triangle right here and this triangle right here, and I said that this was 2, this was 3, this was 2, and this is 3, and these 2 angles are equal, right? If I just had this, right, and I was looking at them, I would see this side is equal to this side is equal to this side, and the angles are equal, you would say these are congruent or equal to each other using side angle side. But couldn't I also check to see if they were similar using side angle side? I could test 2 over 2, compare that to 3 over 3, they both equal 1. Because both of these ratios both equal the same number 1, they would also be considered similar. So any triangles or shapes that are congruent are also similar, okay? Because similar means that they're the same shape, they are just different sizes, or they might be different sizes. So if they're the same shape and the same size, that still falls under the category of similar. But it's not true the other way around. Just because they're similar doesn't mean that they're congruent. For example, right? Oh, not that one. We said that these 2 were similar. They were the same shape, but this one is a different size than that one. So clearly they're not congruent. So just keep in mind, if I ever show you something like this, no numbers, but I say, are these 2 similar? You can say yes. Because anytime that you have congruent shapes, these are congruent by side angle side because of the markings. If they're congruent, they're also similar. Okay, so that's an important concept to remember. Alright, a little bit more practice with these. So for this one up here, I notice that I have 2 angles here, but I only have 1 angle here. When you only have 1 angle in a triangle, you can't find any others. You need at least 2 to find the third one. So I can't add any more angles, so that rules out angle. So I notice, however, that I have 2 sides per triangle. So that's going to tempt me to try side angle side. I can't use side because I don't have all 3 sides. For side angle side, we need to have the 2 sides and the angle in between them. I have that over here, but I don't have that over here. However, I do have these 2 angles. So if I use the 60 and the 40, I can subtract that from 180 to find the third angle that I don't know. And so that would leave me with an 80, which coincidentally happens to be the angle that's over here. So I have the A of side angle side taken care of. All I need to do now is check to see if the sides that are surrounding the angles in each triangle are proportional. So I compare the 2 to the 4, short to short, and then long to long, or longer than the others to, we're just going to call them short to short, long to long. So if I compare 2 to 4 and 3.5 to 7, they both are the same number, they both simplify to 1/2. So these are the same value. That means that the triangles are similar by side by side. Alright, this one looks very blank, but there is an important detail to recognize about this picture. We do have these parallel segments here. And remember, parallel lines or segments give you angles. So if I look really carefully, I can see another Z. Remember, the corners of the Z, the alternate interior angles, are congruent. And then I can also add these vertical angles. You could also do the Z the other way and get these angles, the H and the, what is that, I? These corners right here and right here. You could also say that those are congruent and have all three sets of angles being congruent. But as soon as you have two, you can stop. So these would be congruent by angle, angle. Sorry, not congruent. These would be similar by angle, angle, because I have two pairs of congruent angles. Alright, this is another tricky one. These shapes are overlapping. So again, anytime they're like right up next to each other or they're overlapping, it's a really good strategy to separate them. So I'm going to go ahead and redraw them. So I have the upright right triangle, and then I have the one on its side. They both have right angles. This one has a vertical side of 14, and then total, the bottom would be 12, because I have the 8 and the 4 to combine them together. And then, or sorry. That's the bottom of the smaller triangle. That's my fault. That's this. Sorry, the long side of the right triangle that was toppled over. That's 12, 10, and 8. There we go. So the only time that you use this 4 is together with the 8 to get the 12. Alright, so clearly this one is going to be side angle side that I am testing. So I have the angles already. I can see I have those right angles for each triangle that are congruent. So that's the A part. Now I need to compare short to short and long to long in each triangle. So I'm going to compare 8 to 10 and 14 to 12. Put those in your calculator. You'll notice that this is less than 1 and that is more than 1. So they're obviously not the same value. So if they're not the same value, then these are not similar. And remember, when it breaks the rule, the reason why they're not similar is because side angle side fails. You always have to back up your answer with some sort of reasoning, so make sure you remember to include that. Our last row here. So what's interesting about this one is, again, it has those markings instead of numbers, but there's something special to pay attention to with these triangles. Last time we saw this, the triangles were isosceles because they had two congruent sides, and we used that to find angles. If you look at these ones, they have all three sides are equal. That's equilateral. So this one seems like it doesn't have enough information, but there's actually something we can derive from these triangles using the fact that they're equilateral. If all the sides are the same, excuse me, then all the angles must be the same, right? So if all the angles are the same, and I know that all three angles add to 180, that means that each one of those three angles needs to be 60. So in this triangle, I can take all three of those angles and say they're 60 because it's an equilateral triangle. This one is also an equilateral triangle. It's just the sides are a different length than the original one, but all of the angles are still the same. So in this one, they're still 60. So even though the one equilateral triangle has different side lengths than the other one, I don't know what the sides are. I just know that they're different. We still know that all three angles inside are the same. So I can say that these are similar by angle, angle. I don't need to know the side measures. Again, I just use the fact that they're equilateral to get that all three angles are 60, and I'm good. It's actually important to know that every single equilateral triangle that exists is similar to all of the other equilateral triangles, because it doesn't matter what size how long the sides are. It's a better way of saying it. It doesn't matter how long the sides are. since all the angles inside are 60 every single time, all equilateral triangles are similar to each other. So that might help you if you find this kind of situation. Again, you can say, oh, equilateral, they're similar by angle. You can get it done a lot faster. All right, for this one, for these two, I'm now going to name the triangles I want you to check. So there's no guessing game like you're trying to figure out which triangles I'm asking you to compare. I'm asking you to compare this one to this one. So you just want to look at the picture to find those. So DSY is this one right here, and RSA is that one right there. So it's interesting about those two triangles, they're kissing right there at that point. Does it have a name? Yeah, S. So this point right here, that's where they're touching, and they do have that crisscross kind of relationship here. So I can actually say that I have two congruent angles here. I know it's a little bit squished and hard to see, but I have two congruent angles using vertical angles. So because I was able to add that angle using vertical angles, and I have these sides surrounding the angle in each triangle, I'm going to test side angle side to see if it's going to work out. All right, I already have the A, because the vertical angles give me the pair of congruent angles that I need for side angle side. Now I'm going to compare short to short, long to long. So I'm going to compare 10 to 6 and 18 to 30, because those are the corresponding sides. You can also use the names up here to get the corresponding sides, so it's another benefit to having the names there. But when I compare 10 to 6 and 18 to 30, those are definitely not the same number. And so because those are not the same, that means that these are not going to be similar triangles, because side angle side fits. Okay? Then our last one here, I'm comparing NCB to NAC. So they're right next to each other. Alright? No angles, but each triangle I see all three sides are labeled, I have values, so I'm going to be testing side, side, side. Compare short to short, medium to medium, long to long. So in this triangle I have 9 compared to 12 in this triangle. Then in this triangle, the median side is 12 compared to 16 over here, and then 15 compared to 20. When you put all of those ratios in the calculator, they will turn out to be the same number. They all boil down to 3/4. So because they're all the same, that means that my triangles are similar by side, side, side. Okay? So that's how you would approach these questions if they ask you if triangles are similar. Figure out which rule you want to attempt. Of the 3, you check the information that you have, whether the angles need to be congruent or the sides need to be proportional. You just check to see if the information works and then pick which rule applies. Now we're going to look at some more questions involving solving. So solving is a pretty big emphasis for this unit, so I want to make sure we get more practice in today. So just remember, in each diagram, the triangles are similar. The directions may or may not say that the triangles are similar, so I'm going to show you how you can figure that out on your own. But anytime that you get to the fact that the triangles are congruent and you're asked to solve, you guys are going to use proportions to solve. Remember, anything that has to do with solving or sides in similar figures, solving similar sides, they all start with S, you guys will be using proportions. The only thing that involves congruency when you're working with similarity are the angle measures. Alright, so now again what I was mentioning, I know the directions here say that the triangles are similar, but if the directions don't say that the triangles are similar and they just say solve, you can really quickly check visually to see if they're similar yourself. So if you look here, I have the parallel lines. They said that they're parallel on purpose. That information is not just there for no apparent reason. It is there on purpose. If you have these parallel lines, remember parallel lines give you angles. In this case, it would be corresponding, not alternate interior. So using the parallel, I can say that these two are equal and these two are equal. So using the information in the picture, I can confirm that these two triangles, there are two. You have the smaller one right here, and then the bigger one that's kind of surrounding the smaller one. Both of those are similar by angle. Okay? So whether the directions say that they're similar to begin with, or they've left that out and they've given you the parallel lines and you have to figure it out for yourself, look for that angle-angle relationship with the parallel lines, and once you've confirmed that they're similar, you can move on from there to solve. Okay, so all of these scenarios that I have here, especially these 3 and this one, they're what I like to call nested diagrams, and you're going to hear me refer to that a lot for the remainder of the unit. I was inspired to call them nested diagrams because of the nested Russian dolls. Hopefully you guys have heard of those before, you can Google them. The nested Russian dolls are the dolls that are inside of each other. So like when you take off the head, there's another doll, and then you keep pulling out dolls out of the inside of the previous one. So that's kind of the inspiration that I use to call these nested diagrams. Because if you look really carefully, again, you have a small triangle that's nested inside of a bigger one. Okay? While they're together like this, where one's overlapping with the other, it's a little bit hard to see what corresponds and how to work with the actual measures of the sides. So whenever you guys see a nested diagram, I really recommend that you guys draw the triangles separate from each other. It's a really good strategy. It's going to help you keep the information, the numbers, and how they correspond, keep it more organized, and be able to work with it a little bit easier. So, for example, you don't have to draw them to scale to match the exact same sizes with what's in the picture. Just draw one bigger one and one smaller one. And then you're going to go one at a time. So this is my bigger one. The vertical side over here is 40. The horizontal side is all of this, the 12 and the 48 added together. So that would be 60 total, okay? And then the long side here on the slanty side is the y portion and the 58 combined together. So that would be y plus 58, okay? Whenever you have two pieces to a segment that you're trying to add together and they're not like terms, you just write it as a sum, y plus 58. And then the small triangle, I have x, 48, and 58. So with the triangles separate, it's a lot easier to see what corresponds, right? The x corresponds to the 40, the 48 corresponds to the 60, the 58 corresponds to the y plus 58. It's a lot easier to spot those corresponding parts, and that will help you with what we're about to do, which is writing proportions to solve. So, if I take a look at this one, let's go ahead and start with x, the simpler one. So again, remember our system is to write what you're looking for on the top, the first extreme of your proportion. To write the x, and then underneath that you're going to write what corresponds to that side in the other triangle. So x corresponds to 40, and then the next ratio has to be two corresponding sides that don't have variables, they're just numbers. So that would be our 16 or 48. But since I started in this triangle with the first ratio, I need to start in that triangle as well. So I'm going to have 48 over 60. Instead of 60 over 48. So again, make sure you have them stacked in the correct order. So when I cross multiply relatively big numbers, I trust you guys can do the algebra, the number crunching in your calculator, and figure out those numbers. But you would get x equals 32 after you cross multiply. Now we're going to do y. So I have y plus 58, right? Because y by itself, the variable y, was just talking about this little piece right here, that's not a side of a triangle. That's a piece of a side of a triangle. So you would never just write y by itself. It needs to be combined with the 58 to actually represent a side of a triangle. So that's why I didn't just write y like I did for x. You need to combine it with the 58. So this is one expression that's linked together. So y plus 58 corresponds to 58. I'm going to recycle the 60 and the 48. I just need to make sure that I flip it this time, because I started in this triangle when I wrote the first ratio. And so when I cross multiply, again, large numbers. Okay, so you're going to have to take an extra step to solve this one. You have to subtract the 2784 over, and then divide by 48. And when you do that, you should get y is equal to 2.4. Okay, so I expect you can do those calculations on your own, so I'm not really including them here in the video. So that's how you would approach a nested diagram. So here's another one right next to it. So again, I know that they're similar. I can use corresponding. Aha, they're similar by angle. Here's my larger one. Here's my smaller triangle. So I have 45. And then the full length of my bottom side is the 36 and the 60 added together, which is 96. And then the diagonal, the full diagonal, is going to be the 2x plus 6 plus 5x, which is a total of 7x plus 6. And then for my small triangle, I have y, 60, and 5x. Alright, I'm going to start with y this time. y corresponds to 45. The two sides that don't have any variables that are just corresponding numbers is the 96 and the 60. Since I started in this triangle, I'm going to write the 60 first. And then I'm going to cross multiply. 28.1. That's what I get for that one. Okay? Now I'm going to solve for x. So again, the x is linked with other terms for its expression. So I have 7x plus 6 over 5x because these two sides are corresponding. They're the slanted ones. And then I'm going to recycle the 60 and the 96, but I'm going to do the 96 first. So it comes from the same triangle as the 7x plus 6. Then I'm going to cross multiply and get some large numbers again. So I have 420x plus 360 is equal to 480x. So in this scenario, I have an x on either side of the equal sign. So I need to combine my terms, pull this term over. So I'm going to go ahead and write that. 60. So I just bring the 420x over to the 480 by subtracting. It just leaves me with 60x. And so when you divide, you get 6. Alright. Then we just have this bottom row left. So this next one on the side right here, that is not considered a nested diagram, but you still have to be really careful with how you approach this. With the redrawing, it's still really important. They're not nested because one's not inside of the other, but there's some important information that you might not catch unless you separate them. So still, again, when they're touching in any way, shape, or form, especially when you're trying to solve, it's a good idea to separate them. So I'm going to go ahead and do that. I'm going to have this triangle. Let me try that again. I have that triangle. Did not work any better the second time. And then I have this triangle. Alright, so for this one, I have 2y. I have the 6. And then the full length right here is the 4 and the 5 added together, so that's 9. Sorry, I need to put this somewhere else. I don't have room. Here's the 1, and then... Alright, so I have 9, 2y, 6. Alright, then on the one that's been toppled over on its side, here's the right angle, here's the right angle. This one right here is 4, and then I have y plus 4 right there. I do not know what this side is. So what's interesting to notice about this picture is that in the upright triangle, this one on the left, I have all 3 sides. But on the one that's been toppled over, I only have 2. So it's important that you pick the 2 sides in this triangle that correspond with the 2 sides you have in the other triangle. Otherwise, you're not going to be able to write a proportion. So if I'm trying to solve for y, let's start with 2y. That's the slanty sides. That's going to correspond to the y plus 4. Now I have to figure out of the 9, 6, and 4, which of those to pair up so that they're corresponding. So I noticed that I didn't have this side right here. And if I look really carefully, that's the longer leg of the toppled triangle, and the longer leg of the upright triangle is the 9. So the 9 corresponds to this side that I don't have. So that means that I'm not going to bother using the 9. It's not going to work for me. So I'm going to use the 6 and the 4 as the other 2 values for my ratio. So when I cross multiply, I get 8y equals 6y plus 24. Subtract, divide, get y equals 12. Alright, coming up on the last 2, this one is also a nested diagram just like the 2 and the row above it. It just looks different because now it's a vertical kind of overlapping as opposed to a horizontal line like in the top 2. But you can still redraw and work with it the exact same way that we did for these 2 up here. So if I redraw the top one, and then I redraw the bottom one, this is 11, 10, and x for the top half. Then when I draw the entire, the big triangle that is containing the smaller one, that's going to be this whole side, which is the 5 and the 11 added together, which is 16. The 12 on the bottom, and then the 10 and the y added together, which would be 10 plus y, because they're not like terms, you just have to leave it as a sum. That would be how you would label the larger triangle. So if I'm starting with x, I'll change colors. If I start with x, that corresponds with the 12. And And then the two sides that don't have variables that I would use for the other ratio are the 11 and the 16. So I would use 11 over 16, keep the order the same, cross multiply. I don't know, it's been written down. That would be 8.25. So that's for x. Then for y, the only expression that has y in it is this one right here. Again, I know I'm looking for y, but don't just write y, okay? There is no segment in here that represents the side of a triangle that's just y. The side of the triangle is 10 plus y. You can't separate the 10 and the y from each other when you're trying to solve. Because the y, again, y just represents this. That's not a side of a triangle. To get the side of the triangle, you need to include the 10. So that corresponds with the 10 in the small triangle. And then I'm going to use the 16 and the 11. I have to switch the order. So I get, right, a little bit smaller. So I get to the point where I have 11y equals 50. Oops. Alright, so it has a decimal. It's approximately 4.5. It repeats the 5454 as a decimal. If it's a run-on decimal, just round to at least one decimal point. You can do 2 if you want to. You could also write that. It's fine. Alright, our last one here is a word problem. You guys will be running into a handful of word problems in this unit. You need to be able to draw the picture if they don't have a picture already. Or if they do have a picture, you need to be able to label it and then know how to use that picture to solve. So in this one, we have a tree and a dog. The sun is up here, so it's kind of casting light. So anytime it's talking about shadow, that's going to be in front of these objects. So the dog is 10 feet from the tree. The dog's shadow is 4 feet, and the dog, while it's sitting, is 3 feet tall. I want to know how tall the tree is. So let's put all that information in. It says the dog is 10 feet from the tree. That's this right here. The distance from the tree to the dog is 10. Then it says that the dog's shadow is 4 feet. So from the dog's, where it's sitting out to this point right here, which is where the shadow ends, that would be 4. And then it says the dog itself, while it's sitting, is 3 feet tall. I'm going to draw that little vertical there just to indicate that while it's sitting, it has that vertical tendency. And then I'm looking for the height of the tree, which again is a vertical. So hopefully you guys can see how this picture actually is a nested diagram. The dog out to the edge here is like a smaller triangle, and then the tree out to the point or the edge is also a triangle. So you have a small triangle inside of the bigger one. So a lot of the times these word problems are actually going to involve nested diagrams. Not always, but if they do, you're going to use the same process that we've done before. You're going to draw the triangle separate from each other. So I have the big one, I have the little one. So the tree is x, the full length here is 14, because you're going to add those two pieces together. I have the 3 and the 4. So when I draw this with the triangles, it suddenly makes this problem a whole lot more reasonable, because we're able to work with the triangles and the numbers and the corresponding pieces with a proportion a lot more easily, because we've been practicing that. So when I look here, when x represents the height of my tree, that's what I'm looking for. X corresponds to 3, those are the corresponding sides, and then 14 corresponds to 4. That's how I build my proportion. Then I cross multiply, I get 4x equals 42, and I get 10.5.